So let me take an example of a chemical equation that we can balance. Okay? So let's try an example of a combustion reaction. So the combustion reaction we're going to do is butane with oxygen to form carbon dioxide and water. Okay, so the chemical formula for butane is C4H10. And I'm going to indicate that it's a gas. And then we're going to react that with oxygen gas to form carbon dioxide, again a gas, and liquid water. So there's the chemical equation, and now we're going to practice balancing it. So here's what I recommend when you do combustion. For combustion, do the carbon first, then do hydrogen, and then do oxygen. And the reason you want to do oxygen last is that the oxygen appears in the equation all by itself here. So changing the coefficient doesn't change any other elements. So leaving it for last tends to work. So here's the approach. This is called inspection. What you do is you look on the reactant side first. Remember, these are reactants and these are products. How many carbon atoms are on the left side is what you ask yourself. And if you look at it, it's C4H10, so there's 4 carbons. So we have 4 carbons. Now, look on the product side. There's CO2 and water. There's only 1 carbon, right? The subscript next to the C there's no subscript written, so it's a 1. If there's no subscript, it's a 1. So there's 1 carbon. So that means that there are more carbons on the left side, the reactant side, than there are on the product side, the right side. So here's what you can do. You can put a coefficient in front of any of the chemical substances you want. I'm going to put a 4 in front of the CO2. Now, by putting a 4 in front of the CO2, that changes it from 1 carbon to 4 carbons, right? Does that make sense? Put a 4 in front of it, it now means that there's 4. Okay? Now, there are the same number of carbon atoms on both sides, so we're done with carbon. We go to the next element, which according to my advice would be hydrogen. So how many hydrogens are on the reactant side, the left side? Well, there's a subscript of 10, so that means there's 10 hydrogens. How many hydrogens are on the product side? Well, there's none in the carbon dioxide, but there's 2 in the water, so it looks like there's 2 hydrogens, right? So I'm going to write that there's 2 hydrogens on the product side. There's more hydrogens on the reactant side, right? 10 is more than 2. So we're going to do multiples. If you have 10 on one side and you have 2 on the other, we're going to need to multiply the 2 by some number to get us 10. What number do you multiply 2 by to get 10? 2 times what is equal to 10? 2 times 5 is equal to 10, right? So if I put a 5 in front of the water, that now gives us 10 hydrogens, right? 2 for each water, but there's 5 waters. 2 times 5 is 10. So now we got the correct number of hydrogens. So now the hydrogen is done. The last one is oxygen. Now this is a little tricky. The oxygen can be tricky in combustion reactions, but let me go walk you through it. There are 2 oxygens on the left side, right? But there's more than 2 on the product side. There's 4 times 2. That's 8. And then 5 times 1, that's 5. So 5 plus 8 is actually 13 oxygens. So there's more oxygens on the right side than there are on the left side. So here's what you're going to do. We have 2 oxygens on the left. We have 13 on the right, okay, on the product side. We have to multiply the smaller number, which in this case is a 2, by some number that gives us 13. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. 2 times 6 is 12. So how do we get 13? I'm going to show you this way. 2x equals 13. In other words, 2 times something equals 13. Well, divide both sides by 2 and you get 13 halves. Look at that, 13 halves. So that means that by putting 13 halves in front of the oxygen, 13 halves times 2 is 13. So we now have 13 oxygens, and it's now a balanced equation. Now, you are going to get advice from instructors, from people online, from textbooks, from software programs that tell you no fractions as coefficients. And I'm going to make my little point here, which is to tell you that's nonsense. There's nothing wrong with having a fraction as a coefficient. If you were to take a math class and someone were to tell you that 13 halves x equals y, and they would tell you that that's wrong, you can't have a fraction, you would say, come on, I don't believe that, right? There's nothing wrong with having a fraction in front of the x. The same is true in chemical equations. There's nothing wrong with having a fraction in front of as a coefficient. However, people write exams and people write software programs often for their own convenience. And because of that, it is often inconvenient to have a fraction as a coefficient. So for that reason, it is generally suggested that you mathematically do something to the chemical equation to eliminate the fraction. And the simplest thing you can do is to multiply the entire chemical equation by some small whole number in order to eliminate the fraction. So if I were to do that with this algebraic equation, what I would do is I would multiply it by 2, and that would give me 2 over 2, 13x equals 2y, right? You're just multiplying both sides by 2. So that gets rid of the fraction. You do the same thing in the terms of the chemical equation. So if you have a fraction, and the fraction is a half, 13 halves is 6.5, then just multiply everything by 2. And you would get 2 butanes plus 13 oxygens gives you 8 carbon dioxides and 10 waters. Okay? That gets rid of the fraction. Perfectly fine. This is okay. In my opinion, this is also okay. In fact, I'm not going to argue, but I'm going to make the point that there is a reason that this equation here is superior form to this one. But you may not see that in your textbook, and you may not see that in your software programs that you're using. So they often will prefer this. So if you're asked to do it in terms of whole numbers, that last step, multiplying through by 2, will accomplish that. Now, it's not a bad idea to go ahead and check. If you'd like, after, I'm going to come over down here, because this is a little bit more complicated. There's 2 butanes, so that means there's 8 carbons. There's 8 carbon dioxides, so that means there's 8 carbons on this side. So the carbons are balanced. 2 times 10 means that there's 20 hydrogens. 10 times 2 means that there's 20 hydrogens. In terms of oxygens, 13 times 2 is 26 oxygens. 8 times 2 is 16, plus another 10 is 26 oxygens. So all of the balancing is complete in terms of that. Okay? So you can practice as many of these as you want. I'm not going to show you any more in terms of this lecture, but you will have some practice problems and some sample problems to try. And I do recommend balancing equations is not something you learn by doing 2 or 3, at least most people that's the case. It's best learned by doing 20 or 30 of them. So just like you're learning basic algebra, you have to do lots of examples. Same thing with balancing equations. You want to do a lot of practice problems.